Okay, so the last talk is by Francesco. He's going to talk to us about Sobolev inequalities, concentration compactness, and applications to the generalized Yamabe equation in the non-smooth setting. So please.
Thanks. So good morning. Thanks for the organizer for the possibility to speak. So this is based on two joint works with Ivan Jyvaskyla. So it's mainly based on the first one, which deals about stability kind of questions of Sobolev inequalities in the Riemannian setting. But for the purpose of this, I will present actually application of this theory and techniques to the Yamabe kind of problems. So this, I guess, it's more in line with this part of the workshop. So today's outline, I will start a little bit with some backups of Sobolev inequalities in the Riemannian setting, and speak about this generalized Yamabe problem equation. And then I will move to the no-smooth setting in order to try to get some techniques for an existing theory of these PDEs here, starting from the notion of smooth setting and then going through the Sobolev kind of inequalities and then propose an existing theory. Then I will get to these techniques of concentration compactness in order to get smooth application actually. The last one I didn't advertise because actually it's very recent. So let's see at the end. So my Sobolev inequalities, it's of this kind. So I have two constants, A and B. I get conjugate exponent, and I require this inequality holds on my manifold. So if this holds, I say that these constants, Sobolev inequality constants A and B holds true. And this is the notion of optimal constants here is not really clear because you have two. It's different from the Euclidean setting. And in fact, this program is called AB program. So there is a nice, huge list of, especially in the French school, of people working on the topic. It's non-exhaustive, but let me start on the B part of the program. So you minimize overall possible B for this inequality holds, and these constants, I call it beta, and it's rather easy to see that it is volume with this exponent here. So going to the A part, this constant alpha is the minimum possible constants A for which inequality with constants A and B holds for some B. And notice these are not minimum, just inf. And so the notion of the value of constants alpha was computed by Aubin for compact manifolds. And is precise the squared Euclidean sharp Sobolev constants in Rn. Which was computed by Aubin and Talenti. So my motivation to study alpha here is that it is tightly linked to the local and conical actually geometry of the space, and is tailored to study concentrating sequences for the optimization problem that we will see. And let me present now this PDE. So it's called generalized Yamabe equation. I will say why it's generalized Yamabe in a moment. But for the moment, let's go in a compact Riemannian manifold and consider these PDEs for parameter lambda and then an infinity function S. And I consider this functional here, and I minimize overall possible Sobolev function. I call this generalized Yamabe constants. And Aubin and Trudiger, they showed that there is a comparison with respect to the Euclidean sharp Sobolev constants to the -2. And moreover, a solution of this exists, for instance, in a weak sense, provided the strict inequality occurs here. And let me recall that this is precisely the constants alpha to the -1. So the reason why this strict inequality is crucial for the existence of solution is that this prevents concentration phenomena of optimization sequences here. And this is called generalized Yamabe equation. Also in, for instance, Hebe's book, it's called generalized the Scalar curvature equation, is because it's there is a clear link with the Yamabe conjecture, which is basically asked that whether a smooth positive function exists, such that conformal transformation has constant scalar curvature. So this was solved by the combination of these works, and the solution satisfies this equation. So this S for me in this way is generalized in this equation because here you really have a scalar curvature in the real problem. Okay, So I want to bring all this in a normal smooth setting, and this for two reasons: to propose an existent theory and to get some smooth applications also. Let me start by saying what for me is the singular setting. So it's complete and separable metric space with a reference measure, which plays the role of volume measure. So there is a scalability theory by Lotz, and Villani. You can speak about synthetic Ricci lower bounds. So this is the Kn, K lower bounds, and dimension upper bound by n. And for my goal later, I will also need to enforce a Riemannian condition to the CD condition, which was defined first in the infinite dimensional setting and then later in the finite dimensional setting. And this is basically can be formulated by adding the so-called infinitesimal Hilbertianity to the CD theory. For me, for instance, the Laplacian is linear, would be a nice fix. So there are further contribution around this. Don't have time to mention equivalent definition in terms, for instance, of Bochner inequality, but I want to focus on key properties for this talk, which are the stability in the measure Gromov sense of this condition, and also I need Sobolev calculus in metric measure space. So this is purely abstract. This notion are all equivalent. I don't need the precise definition, but I want to mainly say that you can also speak about Sobolev calculus along metric measure spaces, which are structures which are converging in this weak topology. So you can do this. You can take Sobolev function on Baring space. You can speak about strong weak convergence and also Sobolev convergence. Okay, so let's start with the value of alpha. So let's try to refine things of Oben and Trudinger in this setting. So we consider this very same Sobolev inequality with constants A and B, and we seek the value of alpha in this generalized singular setting. So our first result is that alpha is always greater or equal than the sharp Euclidean Sobolev contrast squared. But here the no-smooth setting kicks in, because as I said, this is kind of the local geometry. So you should expect, and actually there is, the so-called Bishop-Gromov density on the denominator with this red exposed. So the Bishop-Gromov density is just this limit, which exists by Bishop-Gromov monotonicity. And the equality here holds when you have a compact metric space. So let me give just one main idea to prove the greater or equal inequality. So you take a point where the Bishop-Gromov density is finite, you perform a blow up, and if you take radii for which you are converging in some pointed measure Gromov sense, then any competitor for alpha, A, would be actually admissible for a Sobolev inequality in the tangent structure, which of course has to be like a Euclidean case. So this to prove the greater or equal. And for me, it was key to get a precise characterization of alpha, because I want to speak about generalized Yamabe equation in this setting. But recall that S here should I mean, in RCD setting, you don't have scalar curvature, but you really think that if you had, you would put that. So you cannot just propose an existent theory of these PDEs in a no-smooth setting, just saying S is L infinity. And the reason is that you only have Ricci lower bounds, so it's very unnatural to me. And what works is this assumption. So you have an integrable lower bound, and you're absolutely continuous with respect to capacity. So this is important because you can, it's not only is not satisfactory to have an infinity function, but also you need things to be measured, because typically curvature tensors are not functions in this Riemannian curvature dimension condition. So this, my working functional space here, it would be a Sobolev function which has a Laplacian, which is a measure, and also which is L2 of the total variation of S. And my PD would be this one. Notice that this PD makes sense under this assumption, because my function U, it's also defined, this is Sobolev, it's also defined up to capacity null sets. And so in particular up to S negligible or total variation of S negligible sets. So I can multiply, using a little bit of notation, U times S, this is a signed measure, it makes sense to say that the Laplacian is the right-hand side. And so our theorem is the existent theorem that you had in the Riemannian setting. So if you prescribe strict inequality with this of the generalized Yamabe constants, minimizing of this functional, and here the right S. So non-zero, non-negative weak solution exists. And moreover, and here we have to drop a little bit the regularity. So if S is an LP, then you also have a Aubin and Trudinger comparison. So how this can be done? Let me give a little bit of sketch, because this allows me to speak about concentration compactness. So you are naive at start, you try to minimize the functional, maybe you can start trying direct method, for instance. And so you renormalize in unit in 2-star norm, and your assumption were that here was strict inequality. So for instance, it's strict and lambda epsilon. So it's rather easy to see that you have you end up with a W12 bounded sequence. It's converging somewhere up to subsequence in L2. Function limit function is Sobolev, but then you soon realize that you cannot say anything about the 2-star norm. And in fact, it's the critical exponent that basically gives you some difficulties here. So it's also easy to see that there is kind of semi-continuity. So function U is L2 in the total variation of S, but you cannot say anything about the 2-star norm. So now you have to start going back to the concentration compactness in this no-smooth setting. So the key point is that you have a Sobolev inequality by assumption with some constants A epsilon and B epsilon. And you use this to produce a concentration compactness dichotomy. So there are two possible behaviors of these minimizing sequences. So either you were having full convergence in L2 star, or you were developing point concentration. And this is a dichotomy, so you cannot have both of the same at the same time, because there is an underlying strict concavity built in this optimization problem. And the reason is that there is a 2/2-star exponent in the normal left-hand side. So it is nice that my assumption excludes the second behavior. So you end up with just this, and now basically the direct method can keep on. So you have a limit function. So all the functional, was all the norms in the functional were converging, or there was the right semi-continuity. So you get a minimum, you perform Euler Lagrange equation, and you get your solution. Okay. So let me go now to two applications of this concentration compactness techniques. And the first one, it's about continuity in the measured Hausdorff sense of this generalized Yamabe constants. Let me explain what I mean. So you can also think here as smooth manifolds, but in generality, you can take sequence of RCD spaces which are converging, renormalized for simplicity. They are converging the measured Hausdorff sense. Then you have LP functions Sn, which are weakly converging along spaces to some S in LP. And my claim is that the constants pass to the limit. So this was already addressed by Honda in the context of rich limits. The only difference, and actually it's a relevant difference, is that there was an upper bound on the lim sup that was preventing concentrating phenomena. So in some sense, the extreme case was left. And the reason is that you need concentration compactness to handle that. So the idea is, and this is very natural, also if you have smooth manifolds here, you need some Sobolev calculus which is not smooth in the sense that you have to handle together functions defined along the sequence. And of course, these functions will be almost saturating along the sequence. So it is almost optimal in definition of lambda, and this almost optimality gets lower and lower along the sequence. So you are basically in the same framework as before, just that space is not more fixed. So you have to rework with the Sobolev calculus along the spaces this concentration compactness argument. but I'm not saying anything about the limit constant. So I'm not prescribing any strict inequality. So concentration points here may appear. You can deal with that and get continuity at the end. Okay. So second is a problem about so-called problem about stability. So let me start first from the beginning. So you can take a solution of Yamabe problem. It's given by a critical point of this Yamabe functional. So you minimize the very same functional before, just that here you have a really scalar curvature, and I call this Yamabe constant. So from the scratch on the spheres, basically everything is understood. So you have complete characterization of extremal metrics. These are radial functions. There are 3-parameter family of radial functions. So it's given by 2 values and a point on the sphere. These are also, minimum is attained here in this family. And what about stability? So it's a function, it's almost, it's almost minimizing here. So is it close in some sense to this family? The answer is yes. And what is surprising is that you can actually bring the whole Bianchi-Einstein stability of the sharp Sobolev inequality in Rn back to the Yamabe problem on the sphere via stereographic projection. For instance, this was noticed, I guess, in many papers, for instance, also in this one. So this stability is actually quantitative, is sharp, and is optimal in the exponent. There is a strong norm here. And now you can start believing that maybe you can pass this kind of question also to a more general manifold. So there is a quantitative stability also for general manifold, which is the deficit control, the W12 distance. Also, I'm not going to speak about this too much because what is important for me it's that the class of extremizer in general manifold, they're not really they're not. You cannot say what are, just on the sphere is very special. But I want to propose a stability which is different in flavor to the other one. And the reason is that, so I want to compare actually in a very special situation, almost extremal functions to a radial family of functions, which is the one on the sphere, but which on my manifold is not. They're not extremals. So this is the setting. So the stability is qualitative. So for every epsilon and dimension n, there exists a delta, such that, so given an n-dimensional Riemannian manifold, which is which has n-1 Ricci lower bounds, then you get non-zero function W12, and these are so the manifold was delta close in Gromov sense to the sphere, and the function was delta extremizing, so the deficit is small in the Yamabe functional. And we proved that the function is in W12 distance, it's epsilon close to the family of radial functions, but these are set on the manifold. They are the one extremal on the sphere, but are set on the manifold. Yes, so the proof here is again based on concentration compactness techniques, which are not smooth, and this is natural because if you want to prove this, you go by contradiction, and you end up very naturally with a sequence of Riemannian manifold, with a sequence of functions which are defined along the sequence, and then again you can develop point concentration, or maybe you can you could have converging L2 star. But the point is that different from the applications that I gave you before, so you're not anymore satisfied here just by saying, okay, you developed 1 point concentration, because here you want to study qualitatively the shape of the function. So you need to restore compactness. It's not anymore sufficient to just say there was concentration. So this is the main challenge, and this is actually our latest preprint. The challenge is that you have to restore compactness, and this does not mean that compactness can be restored within the same geometry of the space. So if you the point is that if you are concentrating, that you need to choose right scalings and points where the function is concentrating, and then trying to do a blow up along the sequence in order to recover compactness in some limit cone. This is, I guess, all I wanted to say, and thank you for your attention.